Dear students, next chapter is centrifugal pumps. So the centrifugal pumps are the rotodynamic machines that converts the mechanical energy of shaft into the kinetic energy plus the pressure energy of water. Okay. Now this may lead to the raise the level of water. Now the wheel in which this energy transfer takes place that we call as impeller. So in case of turbine, the wheel where energy transfer takes place is called runner. However, in case of centrifugal pumps, the wheel where energy transfer takes place is known as impeller. Now, a centrifugal pump is named so because the energy added by the impeller to the fluid or to the water is largely due to centrifugal effect. That's why such pumps are called centrifugal pumps. Now, the principle of working of centrifugal pump is same as that of our reaction turbine, okay, but it works in reverse direction. So that means in case of turbine, the pressure energy of water is converted into the mechanical energy of the shaft. However, in case of pumps, centrifugal pumps, we convert the mechanical energy of the shaft into the kinetic plus pressure energy. So the major part over there for the energy is the pressure energy. So that is the main difference between the turbines and the pumps. So you can say the centrifugal pumps works in reverse direction as that of reaction turbine. So centrifugal pumps works in reverse direction as that of reaction turbine. Now the transfer of energy in the impeller is given by the fundamental equation that is called Euler's equation. So the energy transfer per unit mass that we can write as VO square minus VI square divided by 2 plus UO square minus UI square divided by 2 plus VRI square minus VRO square divided by 2. Now, in this equation, the first term represents the change in kinetic energy of the liquid. This is change in kinetic energy of the liquid, that is water. The second term represents the pressure change from centrifugal effect. Centrifugal effect. Okay. And the third term representing the static pressure change due to relative kinetic energy. Okay. So you can say the second and third term collectively represents the static pressure change of the liquid. Okay. So now we can conclude that now the energy transfer per unit mass. Now we can say the energy transfer per unit weight. So that is my head H is equal to, I can write it as VO square minus VI square divided by 2G plus UO square minus UI square divided by 2G plus VRI square minus VRO square divided by 2G. So I simply write this H as equal to VO square minus VI square divided by 2G plus PO minus PI divided by 2G. So this head H, so I can call it as theoretical head. This is my theoretical head, which is the sum of two heads. One is the velocity head, and second is the pressure head. Okay, or you can say in the centrifugal pump, the total head raised sum is equal to the velocity and the pressure head. So the first term in this equation is the velocity head, and second term is the pressure head, and that is my total head H, and that is called as theoretical head. Working of centrifugal pump. So in this diagram, first you see the various components. So here you have the sump. This is the sump. Okay. So this is the reservoir for the water from where we have to lift that. So that I call as sump. Okay. Now in the sump, I have two components. One is the strainer, and second one is the foot valve. Strainer and foot valve, they are connected at the bottom of a pipe, and the pipe is called the suction pipe. Okay. On the other side, I have one more pipe that is called delivery pipe. Okay. So to control the discharge in the delivery pipe, I have the delivery valve. Okay. Now my suction pipe connects to the impeller. Now as you can see the impeller over here. So my suction pipe connects to the impeller at the part. That part is known as eye of the impeller. Okay. So my suction pipe connects to the impeller at the part. That part is called eye of the impeller. So that is along the shaft of the pump. Okay. That is along the shaft of the pump. Okay. Now the impeller is enclosed in a casing, and further the delivery pipe connects to the casing. Now in case of centrifugal pump, we have one more valve that is called priming valve. So these are the various components of this pump, centrifugal pump. Now you see how this pump works. Now in case of centrifugal pump, the water enters the impeller through the eye of the pump. So you can see here the water enters through the eye. Okay. So the water enters the impeller through the eye of the pump, a passage along the shaft at the center of the impeller, and is pushed towards the periphery by the centrifugal force. So when water comes at the center along the shaft, after that it comes in the outward direction. It comes in the outward direction. Okay. So that is along the periphery towards the outlet. So water is coming out now under the effect of centrifugal force. So my impeller rotates. Due to the rotation of that impeller, the centrifugal force is acting on the water which is coming into the impeller. So due to that centrifugal force, the pressure energy as well as the kinetic energy of the liquid or the water increases. So the transfer of energy from the impeller to the fluid takes place within the impeller by the centrifugal effect, which gains in kinetic energy as well as the pressure energy. However, the high velocity, now here the fluid we got. So here now I have a fluid along the casing. Okay. Now this fluid have high velocity, or you can say high kinetic energy plus pressure energy. Okay. Now my requirement is the high value of this kinetic energy is one type of wastage. So I have to reduce that. Okay. So the living water is not desired with high kinetic energy, with high velocity. That is one type of energy loss. So therefore, the kinetic energy gained in the impeller of a pump is partially converted into a useful pressure energy with the help of this casing. With the help of this casing. So we make this casing again of a special type whose passage is gradually increasing from one side to the another side. Okay, so that special type of casing is called volute casing. So this helps in further gain in pressure energy of the water or the liquid. Okay, this is how this uh, centrifugal pumps. So after casing, the water goes to the delivery pipe, and we can control the discharge in the delivery pipe with the help of delivery valve. Now the next question arises: why the pumps are less efficient than turbines? So there are two reasons behind this. Now the first is the type of flow in a pump differ from that in the turbine. So in a turbine, the flow of liquid is convergent. In case of turbine, the flow is convergent. However, in case of pump, the flow is divergent. Convergent means from from higher cross sectional to cross sectional area to lower cross sectional area. Or in case of pump, you can see it is from the eye, which having a lower cross sectional area, to a large part of casing having larger cross sectional area. So you can say in case of turbine, the flow is convergent. However, in case of pump, the flow is divergent. Okay. Now the second thing is, in case of turbine, the flow takes place. So flow is from high pressure side to low pressure side. Okay. In case of pump, the flow is from low pressure side to high pressure side. Okay. Now you can see in a divergent flow, there is a chances of flow separation. Okay. So flow is separating from the blades. So that's why the eddies are formed. When eddies are formed, the eddy losses are created. So that decrease the efficiency of a pump. So flow separation, okay, that forms the eddy losses. So that's why the pumps having, you can say the pumps are less efficient than the turbines. Okay. The next is the classification of centrifugal pumps. So the pumps are classified on the basis of working head. Okay. Number two, specific speed, type of casing. Number four, direction of flow of water. Number five, number of entrance to the impeller. Okay. Number six, position of shaft. Okay. And the last one is the number of stages. Now the first classification. on the basis of working head. So on this basis, we have three different types of pumps. One is low head centrifugal pump. The second is medium head centrifugal pump. And the third is high head centrifugal pump. Okay. So the low head centrifugal pump, this is normally a single stage pump. So here the working head is below 15 meters. Okay. So such pumps are used with spiral or volute casing without guide wings. Okay. So these pumps can be either single section or double section. Okay. Then the medium head. So here the head lies between 15 meter to 45 meters. Okay. So these pumps may or may not be provided with guide vanes. Usually these are the single stage pumps, and these can be either single section or double section. Then the third one are high head centrifugal pumps. So here the head is more than 45 meters. Okay. So these pumps are known as high head centrifugal pumps. So these pumps are normally multi-stage pumps. These are multi-stage pumps and are provided with guide vanes. Okay. Now these pumps may have horizontal or vertical shafts also. Okay. The vertical shafts are usually used in deep wells. These are used to taking out the water from deep wells. The next classification is on the basis of specific speed. Okay. So just like a pump, we can also classify the just like the turbines, we can also classify the pumps on the basis of specific speed. So in case of pump, the formula of specific speed is n under root of q h raised to power 3 by 4, and its definition is the specific speed of a pump is defined as the speed of metrically similar similar pump which delivers unit discharge under unit head. So this is the definition of specific speed of a pump. Okay. So depending upon specific speed, we have different ranges. So you can see that range from the table. So I have the radial flow, then mixed flow, then the axial flow. Okay. So in radial flow, I have three stages: slow, medium, and high. And here the range of specific speed is, so for slow it is 10 to 25, for medium it is 25 to 45, for high it is 45 to 70, and for mixed flow it is 70 to 135, and for axial flow it is from 100 to 425. Okay, so with the help of this table, by finding out the specific speed, okay, by finding out the specific speed, you can see which type of impeller we can use in a centrifugal pump. Okay, so this table helps us to deciding the type of centrifugal pump on the basis of specific speed also. Okay, then on the basis of casing. type of casing. So depending upon this, we have three different types of centrifugal pumps. One is volute chamber pump. Okay, or simply the spiral chamber pump. So that is something like I have impeller. So that is surrounded by a casing. Okay. So here I have the shaft. Okay. So from impeller, the water is coming out. So this shape of casing is the volute shape or the spiral shape. So in this case, you can see in the direction of rotation, this is the direction of rotation of the impeller. In the direction of rotation of the impeller, the cross section of casing gradually increases. So you can see this cross sectional area gradually increases towards the delivery site. Okay, so this is the volute chamber, spiral chamber, not the vortex one. Now, next type is the vortex chamber. So, this chamber you can see is the volute chamber. Okay, now the second type is vortex chamber. Now, you can see this diagram. So, in spiral or volute chamber, you can see in this case there is some additional space that we call as vortex chamber. So you can see here this additional space that I call as vortex chamber. Okay. Now this vortex chamber is uniformly increasing area providing between the impeller and the outer periphery or the outer volute casing. So on leaving the impeller, the water first goes to the vortex chamber and then it goes to the vortex or goes to the volute or spiral chamber. Okay. Now this extra space provides us smooth shifting or smooth directional change of water which is leaving the impeller. Okay. So this extra chamber you can see increase the pressure energy as compared to the pressure energy available in vortex chamber pump. Okay. So this is my vortex chamber. So here the rotation in the vortex chamber is free vortex. Okay. That is free vortex motion. Okay. The next is, so the third type of pump, depending upon the casing, is the diffuser pump. Okay. So in a diffuser pump, the guide vanes are arranged at the outlet of the impeller vanes. So instead of this dotted line, so along this whole dotted line, okay, so there is a row of blades. Okay. So such pump become a diffuser pump. So the water enters from the impeller to the guide vanes and then it goes to the casing. So again, there is a simple casing that is the spiral or volute type of casing. Okay. Now, when you have the guide blades instead of this free vortex chamber or vortex chamber, now further you see there is a smooth change of direction of flow from the fluid going out from the impeller to the casing. So hence it further increase the efficiency of the pump. It further, you can see, reduces the losses in the pump. Now, when you see the construction of this diffuser pump, this is similar to that of a reaction turbine. Okay, this is similar to that of a reaction turbine. Okay, so this diffuser pump we can also call it as, that's why we can also call it as reaction pump also. This is also called a reaction pump. Okay, so this is the third type of pump depending upon the casing. So first is the volute or spiral chamber pump, vortex chamber pump, and the diffuser pump. Then next classification is fourth one, on the basis of direction of flow of water. Okay, so depending upon this, you can see we have three different types of pumps. One is called radial flow. The second one is the mixed flow, and third one is the axial flow. So radial flow is one in which the flow is completely in radial direction within the impeller. Okay, so this type of pump is used when there is a requirement of high head, low discharge. Okay, then in mixed flow, so here the direction of flow of pump changes from pure radial axial. Okay, so this is used for medium head and medium discharge, used normally in irrigation purpose. Okay, then axial flow pump. So you can see here the direction in the impeller is purely axial. So this is not the case of a centrifugal pump, you can say, because in this case, on the water, the pressure increase is not due to the centrifugal effect. Okay, so but we have such type of pumps also. So this pump is called the axial flow pump. So this is normally used when we have low head, then there is a requirement of low head and high discharge. Okay, so you can see these pumps, the axial flow, these are similar to your propeller turbine. Okay, so if in this case we use uh, the vanes which are adjustable, the blades of this impeller, if that are adjustable, we can call that pump as the Kaplan pump. Okay, that pump we call as Kaplan pump. So that is completely reverse from the Kaplan turbine. Okay, so you can see on the basis of direction of flow, we have three different categories of centrifugal pump. Then on the basis of number of entrance. So on the basis of number of entrance, we have two types of pumps. Okay, one is called single section, second one are called double section. Okay, single section pump and double section pump. So you can see here from the eye, water enters from one side. Okay, one side of the impeller. So you can see in this second diagram, the water enters from both sides of the impeller. Okay, so this case is double suction, and this is the single suction pump. Okay, and then sixth one is on the basis of position of shaft. So depending upon the position of shaft, we have uh, vertical shaft, centrifugal pump, and second one is horizontal shaft centrifugal pump. Okay, so normally we have horizontal shaft for the centrifugal pumps. Normally we have horizontal shaft. However, in case of deep wells, we can use a vertical shaft centrifugal pump. Okay, and then the last one on the basis of number of stages. So according to this classification, we have either single stage centrifugal pump, or we have multi-stage centrifugal pump. Okay. Now, in case of multi-stage pumps, we have more number of impellers, more than one impeller that are mounted on a single shaft, and in between two impellers, we have a row of guide wings. Okay, and that set we include in a, or we enclose in a closed casing. So that becomes our multi-stage pump. Okay, so these are the different types of, or different classification of centrifugal pumps. The next is various components of centrifugal pump. Now you see the various components. The first important component of centrifugal pump is impeller. So impeller, you can say, is the part of centrifugal pump where energy transfer takes place. So it has a number of vanes. So that vanes will be either forward curved or backward curved. The meaning of these two terms we can discuss further. Now, if we talk about this impeller, we have three different types of impellers available in centrifugal pumps. So that you can see in another diagram. Now you can see this diagram. So here we have three different types of impellers. Okay. So the first one is the closed impeller. This is closed impeller. So when the vanes of the impeller are covered with plates from both the sides. Okay. So that we call as closed impeller. Okay. The vanes are covered from both the sides with the plate. That we call as closed impeller. So in case of closed impeller, better guidance to the water, and this type of impeller is more efficient as compared to the other one. Okay, now the material for this impeller is normally the cast iron. Now the second type is the semi open. This is semi open impeller. So here you can see in this diagram we have one side of the impeller vane is covered with the plate and other side is open. So it can be used when the liquid is blended with some highly viscous solid mixture. highly viscous solid mixture is mixed with uh, your water. In that case, we can use semi-open impeller. Then the third one is open impeller. Okay, so it is an impeller without cover plate. You can say this is an impeller without any cover plate. So when the liquid contains more solid suspended matters like sand, okay, paper pulp, okay, something like that. So in that case, we can use the open impeller. Okay, so these are the different types of impellers we have. The another important component of centrifugal pump is the casing. Okay, so that we already seen that depending upon we have three different shapes of casings: volute or spiral casing, vortex casing, and the diffuser casing. Okay, then the another component is suction pipe. So this is the suction pipe. So this is a pipe which connects the sump to the impeller. So this is a pipe which connects sump to the impeller. Okay, so you can see its lower end is dipped into the sump and its upper end is connected at the eye of the impeller. So at the lower end of this suction pipe, we have two component. One is the foot valve, another one is the strainer. Now the strainer is one type of filter which separate the debris in the water. So it also prevent to move those debris into the impeller to avoid damage. So another component is the foot valve. So this foot valve is a unidirectional valve. Okay, in this valve, the water goes only in one direction. So that is from bottom to top. So this is a one type of non-return valve. Okay, so it does not allow the water to go back into the sump. This does not allow the water to go back into the sump. Another component is the delivery pipe. Sorry. Okay, so this is the pipe which raises the water from the outlet of the pump to the required height. Okay, which takes the water from outlet of the pump to the required height. So to control the discharge through this delivery pipe, we can use a delivery valve. Okay, we can use a delivery valve over there. Now, next you see how we start this centrifugal pump. Okay, how we start this centrifugal pump. So to start this centrifugal pump, first we do priming. So to start this pump, first we do the priming. So now what is this priming? So now you can see when I start my centrifugal pump with the help of some motor, the impeller of the pump rotates and produce a forced vortex. Okay, so in the impeller, I have now the air only. So as long as the impeller rotate in the air, the centrifugal head developed by this forced vortex will be proportional to the density of air. Okay, so within my impeller, there is only air. Okay, so whatever pressure is produced, okay, that depends on the density of air. Okay, now this pressure produced, this head developed, now is not enough to raise the water level to the required height. Okay? It is not that much head over there which takes water from the sump to the impeller and deliver it to the required height. Okay. Now what we have to do now? Now we have to remove this air from the impeller. Okay. So removing of that air from the impeller, that we call as, okay. So for that, now what we do? We have to put now some water either from delivery side or by any mean to the impeller. So we have to fill first that impeller with the water. And then at the time motor starts, head develop is now with respect to the density of liquid available within the impeller, and that is high enough to take water from the sump to the impeller and then from impeller to the delivery side. Okay. So the removing of air from the impeller, that we call as priming. So to do priming, we provide one valve in the centrifugal pump, that is called priming valve. Okay. So when the priming is completed and the motor is started, the delivery valve is closed so that the starting torque is required, is reduced. Okay. Now, if the delivery valve is open and the speed of the impeller is sufficient, the water will start pouring out on the delivery side. So this is how my centrifugal pump starts. Okay, so before starting a pump, before starting the centrifugal pump, we have to do priming. Okay.